Okay. So today we are going to do two things. Let's be mindful of that. Let's also look at the time that we have. I want to do cover two things today. One is the assumptions of linear regression. Second one is if you do a machine learning problem, how do you uh, present your results in a powerful medium? I'm going to talk about an app called Gradio. We will build a machine learning model and then we'll try to deploy it using an app called Radio. And it's a powerful medium of showing your insights, showing your predictions to your bosses or stakeholders, clients, and so on. We'll try to cover these two things. If not possible, we'll take that over to next week. All right. So with that, let's start today's session. I'm going to start with assumptions of linear regression because that is very important, and not many people pay attention to these assumptions of linear regression. Okay, is my screen visible?
Yes, sir.
Okay. Uh, I'm going to I'm going to be a little quick here because these are the things that you're already aware of. I'm
Sir,
going to
visible but not legible, sir. Please
understood.
increase the size, sir.
Sure. We'll do that. Is it better now? Is it better now?
Yes, sir. Yes.
Okay.
Yes, sir.
Okay. Let me also show you the data that I'm going to use. Right? It's a cooked up data. X1 has no meaning, X2 has no meaning, 3 no meaning, and the target also has no meaning. It's a cooked up data just to demonstrate the assumptions of linear regression. I'm importing certain packages that you're aware of. Some you might be aware of, some you may not be aware of, but we'll look at them. And I'm avoiding the warnings. I'm reading the data frame, which is data3.xlsx. And if you look at the dimension of this data frame, it's 200 rows and 5 columns. So what are the 5 columns? X1, X2, X3, X4, and then the target variable, which is Y. This is how my data frame is looking. X1, X2, X3, and Y. I have my target variable named as target, and I'm splitting them as X and Y. And I do train test split here, where 70% goes to my train and 30% goes to my test, right? And I'm going to use this model called ordinary least squares, right? And then I'm fitting this OLS model. I know this is fast, but these are simple things. I'm going to send you this file immediately after the class, and tomorrow you can run this and see it by yourself. Okay. So what are we getting here? What are these result.params? What are they giving us?
The coefficients for the
Okay.
model.
So this is your intercept. These are your slopes 1, 2, 3, and 4. Okay. So now let us print the OLS summary. Okay. Now let us understand what this model has done. Okay, what are the important things that we look at as a business analyst or as a business analyst? What are the important metrics that we have to focus on?
R square,
Okay,
obviously,
very good.
that's the
R
goodness
square.
of
So
it.
is this okay? Is this R square fine?
Very good R
Point.
square, yeah, 0.9.
Okay.
Adjusted R square when you're using MLR because, like, if you
Yeah.
compare, you'll be able to see how much it's a more reasonable estimate.
Okay. Fine.
P-value of the F statistic because that will tell you if your regression is significant or not.
Okay. Regression is significant or not? Okay. Okay. So where is the p-value and what do we infer from the p-value?
That prob F statistic, the fourth one,
From where is it? What
in
what
the
are you
in the
talking about?
top part, yeah, that.
Okay. Fine.
And it's very low. So at any
Okay.
level of like most very small level of significance, also you will conclude that it's significant.
Okay. Good.
So the model is significant. Then
Sure.
you can also look at the p-values of the coefficients as well,
Okay. What does that tell you?
whether
P-value of
the
the coefficients.
coefficients are zero or not. So if it's significant, then the coefficients are not zero, in which case your estimates are valid. Whereas if it's not significant, then your coefficient is you can't reject the null hypothesis that the coefficient is zero in the regression.
Coefficient is zero. Okay. So here we have a p-value associated with these are the p-values. Constant has a p-value of 0.091. What does this say? Is it significant or insignificant?
It's significant at 10% level of significance.
Okay, so let's keep the significance level as 5%.
Then no.
Okay, so there is some problem associated with our model because let's say x1 has a value of greater than 0.05, and look at x3. X3 again has a value of 0.3, which means you cannot include x1 and x3 in your model. Is that correct? Is that the insight you derive from this simple OLS regression?
Yes, sir. That's correct.
Fine. So when you what we did a simple step. We had the data, right? We don't know what x1, x2, x3, x4, x and y is. As soon as we got the data, what we did, we split it into test and train, and then we fit an OLS model, and then we see these numbers. It tells us a story that, well, x1 and x3 are not significant, which means we cannot include them in the model. And we have another test called Durbin-Watson statistic. Is anyone aware of this particular statistic?
Autocorrelation?
Yes, it talks about autocorrelation. Do you know the range for this Durbin-Watson statistic?
2, sir.
2, yeah.
Uh, 2 means there is no correlation, no autocorrelation. When it is 0, it is positive autocorrelation, and then when it is 4, it is negative autocorrelation. So we have somewhere around 2, which is okay. But the major problems are the p-values of x1 and x3. So let's see what is happening inside our data set, right? And I have something called X test where I'm going to predict. Okay. I have X test, and then I'm going to store my predictions into Y pred, right? And then I calculate residual. What is residual?
Y minus Y hat.
Okay, Y minus Y hat. Understood. So you calculate residual. Okay. Let's see what is this multicollinearity.
Multicollinearity is where your dependent variables are correlated with each other.
Yes, your features are your in your input variables, independent variables, when they have correlation among themselves. That is, in this data set, right? Ignore y. This is your target variable. When x1 has a correlation with x2, or x2 has a correlation with x4, and so on. When these 4 variables have correlation between each other, then it leads to a concept called multicollinearity. So, what is wrong with multicollinearity? Can you give me an example of multicollinearity?
So, like for instance, if you are measuring the performance of a student, like if you're
Okay.
trying to regress using those variables,
Mhm.
like if a student has a high GPA in one subject, it's very likely that they're going to have a high GPA in some other subject as well.
Mhm.
Or like if in class 10 they perform really well, then it's likely that they'll perform very well in class 12 as well. So there'll be some correlation between the two,
Mhm.
in which
Yep.
case you're not getting any, you're getting a redundant explanation of the variance in what you're trying to predict from the second variable. So
Okay.
it's
Yes.
adding unnecessary noise.
Okay. Okay. So it kind of leads to double counting. That's what multicollinearity does, and it hinders. I mean, it is going to reduce the model performance. So that's what multicollinearity does. Another good example of multicollinearity is, let's say IPL is coming soon. So let's say you want to predict how much runs that Rishabh Pant is going to score. This is your target variable. You want to predict how much Rishabh Pant is going to score. What are the features that you're going to use for predicting the runs that he's going to score in this season? Can you tell me some input features that you're going to use?
Like strike rate,
Okay, strike rate, then number of runs, total runs scored so far,
total runs, yes.
total sixes, number of sixes, number
Four.
of fours, right? Average.
Yeah.
Okay, so now tell me this: if the number of runs, the number of sixes and total number of runs, are they correlated? More number of sixes, more runs.
Yes.
More number of fours, more number of runs.
Yes.
So are they correlated?
Yes, they are.
So yes, so these are typical examples of multicollinearity. So one maybe you can reduce some features for enhancing the model performance. So that's what we use this VIF for, to check multicollinearity between the features or independent variables. So what is happening here? You see something strange happening. So I use an inbuilt function called variation inflation factor. In fact, I have imported that package here. It's available under stats models. And don't worry, I'm going to give you this. I'm going to give you this by tomorrow, and you can run this and test it by yourself. Right. So this is going to give us the variation inflation factor for each and every variable. You see here, x1 has an unusual value of 17.54 because it has a strong correlation with some other variable. So the range for VIF is somewhere between 0 to 10. 0 to 5 means very less multicollinearity. 5 to 10 is medium multicollinearity. Greater than 10, it has a very strong multicollinearity. So now you know that x1 has a very strong variable. Very strong. It is highly correlated with another feature. So what do?
You can create a.
Drop it.
You can drop it directly. Yeah.
Yes. So which one do you drop it? Do you drop x1 or x3?
X1.
So X1.
Okay. So this is a very, very, very difficult question. Right? You need subject matter experts here. Because right now in our data set, we don't know what is x1, we don't know what is x2, what is x3, x4, and so on. So here, this is where you need to closely work with your business managers. You need to understand what is x1, what is x2, what is x3, what is x4, which is more important for business, right? And you don't know with which variable x1 is highly correlated. Is it with x4 or x3 or x2? So you will have to experiment with by removing different variables and then check whether your p-values are getting better and so on. So that's the experiment that you might have to do. So right now you see that x1 and x4 might be highly correlated. You could remove any one of the four. Any one of the two.
Probably,
X1.
sorry to interrupt in between.
Yes.
Probably it could be also be like when you have mentioned that it's impacting a business decision. So you may not remove any of the variable, but you may try to see how the data was collected because the questions were highly correlated. That's why the responses came up like that.
Mhm.
Maybe something in the wrong in data collection method, something wrong in how the researcher
Possible.
collected it. Maybe you have to modify your questionnaire, and then the variables have to be redefined so that they don't have much multicollinearity in between.
Pretty much possible.
So
This happens all the time.
so the problem starts with the questionnaire development from how the data has been collected.
Yes.
And if you
Yes.
directly reject or come to a conclusion like X1 should be dropped, then it would be a blunder. Like maybe for a business, it could be the most important factor. Like let's say product price, place promotion. If you and you drop the product, then there's no
Mhm.
use of taking an estimate of the rest of the three products because your product is not existing. So dropping
Very true.
something, as you mentioned, with the business domain knowledge is very important, not merely playing with the data tools.
Very true, very true. Very well said as well. So this is how you check for multicollinearity. So the ideal thing that you do here is you can either drop x1 or x4. You can try with both. Once you drop x1, run the model with x3, x4, and x2. Build a regression with this and predict your y. Then in the second time, you keep x1, remove x4, and then build another regression model. Look for your R square. Is it improving better or not? Certainly, there is going to be an improvement in the R square, right? If you get rid of multicollinearity and then build a model, it is going to enhance your model performance. There is going to be a slight improvement in your R square and adjusted R square. And this is an experiment. This is an homework that is non-graded for you. You can try it out and then tell me. Uh, this is the first test that you can do multicollinearity. Next one is you plot the residual. And how does it look?
Normal enough. Like
Yes,
not
errors are normally distributed. Okay. So what is the other test that you can do to check whether the errors are normally distributed? Is this a perfect normal distribution?
not exactly, but it's
Slightly left skewed.
Slightly left skewed. How would you confirm whether it is a normal distribution or not?
So
One
we
thing
can
is
check the
visual median.
kurtosis score.
Which one?
So the kurtosis score. If
Kurtosis.
it's 3, then it's normally distributed.
Okay. Okay. That is a very good idea. Kurtosis. Any other statistical test that you are aware of
So
to
the
check whether,
residuals, right? You can use Goldfeld quant. You can use the
what is it?
Goldfeld quant test for normality of residuals.
Yeah,
It's
you
not
have a
there, but
couple of statistical tests which you have already learned. One is the chi-square goodness of fit. You have done it
right.
for uniform. You have done it for uniform. You've done it for Poisson.
Hmm.
Maybe you can try another chi-square goodness of fit for normal distribution. And you have another test called Kolmogorov-Smirnov test. Right? All these things can statistically give you assurance that the errors are normally distributed. Right? What is this homoscedasticity?
Constant variance of the error terms.
Hmm. Okay. Okay. So what is the x-axis here? What is the x-axis?
X-axis is your fitted values,
Your
and
predicted values,
yeah,
and your
and y is
y-axis are
your
the
residue.
residuals. So let's say your x-axis is nothing but your predictions, and y-axis is your residuals. And when you plot them, do you see any evident pattern? What pattern do you see here? It's a bell-shaped pattern, right? The variance keep increasing as we increase the we increase the as we go towards the right. As the intensity increases, what happens to your variance?
Variance also is increasing.
So you see a bell-shaped pattern there. So this is heteroscedasticity. So when you have heteroscedasticity, it violates the assumption, one of the assumptions of linear regression. So look at our plot. You see any evident pattern? More or less, no.
It's random enough.
More or less random, but not perfectly random. Next, what does this mean? Autocorrelation.
Autocorrelation is when, like, if you are collecting any time series data, then like if your errors are repeating themselves, like they're correlated with the shifted
Hmm.
version of themselves, then that
Okay.
is called autocorrelation.
Okay. First of all, let me open my whiteboard. Understand a few things because for some people it might be new. Some of you might already know it. Okay. So you have two types of data. One is cross-sectional data. Other one is time series data. What is the difference between cross-sectional and time series? Give me examples of both. And this data that we are talking about, what kind of data it is?
I mean, so considering like we don't know what the variables are
Hmm.
indicating, we can't really tell what kind of data we've collected, right?
Hmm.
But
So time series data is stock market data kind of thing, sir. Every
Yes.
day it will
Yes.
be increasing.
Okay. So if you collect data over regular intervals of time, right? Then it is time series data. For example, so a gentleman mentioned stock market data, right? Stock market data. Let's say your automotive sales, you get it on a monthly basis, right? Automotive sales, right? You collect it on a monthly basis. This is available at a daily level. Another interesting thing to say is, let's say you have data, your x-axis is always the time, right? Let's say this is, India sales, right? Or let's take Tata Motors sales, right? This is connected in 2024. So January, Feb, March, all the way till October. So here, the difference between Feb to Jan is same as the difference between October to September, right? So you collect data over constant interval of time, over regular intervals of time. It could be weekly data, it could be monthly data, quarterly data, half yearly data, and so on and so forth. Whereas here, you don't have any particular time period. So you can collect uh, at a particular snapshot, right? So maybe you look at the stock price today, right? After 3 days, you again uh, look at the stock price of a particular stock, right? Let's talk about a particular stock, Reliance, right? Reliance stock price, right? Plus 3 days. Then after 15 days, you again check and collect the data, right? There is no time interval, regular time interval. Randomly, you check for the stock price and then you try to build a model. It may not come under the assumptions of time series. Here you have a regular interval of time. So that's the difference between cross-sectional time and cross-sectional data and time series data. So most of the models that we use in machine learning, right? Most of the algorithms that you are aware of, linear regression, right? What else? Let's talk about continuous target variable, right? XGBoost, uh, right? All the bagging, random forest. For all these models, the type of data that you're going to use is cross-sectional. So some people, even when you have time series data, they convert it to cross-sectional data and then do predictions. So that is pretty much possible. So here we were talking about autocorrelation. So here, what is this y-axis? What does this tell you? +1 to -1? What does this tell you?
Correlation coefficient.
Okay, okay. So let's talk about an example. Okay. So gold price, right? Gold price. So today's gold price was high. Today's gold price was high. It is in the upward trend. What is the probability of gold price going high tomorrow? Is it going to be high or low? Today it was high. Tomorrow is it going to be high? Any idea? It could be a guess. We don't want the right answers. We want guesses. Today it was high. Okay, we'll take another interesting example. Rain. Probability of rain. Today it rained. Will tomorrow it rain? Given that today it rained, will is there a chance of getting rain tomorrow?
Maybe.
Probability
Yes,
is
it,
zero.
it may rain. Depends
It
on
may
some
be.
probability.
Yeah. Is that probability high or low? That's what I'm asking. I'm not asking you an exact number. Today it rained. What is the
Again,
probability?
Low, sir. Low. According to this month, actually, it is low.
I'm asking you general trends.
High.
yeah, it might rain.
It
Yes,
might
you can
rain.
say yes.
Okay. Okay. So what does this graph tell you? So what is one correlation mean? Correlation is equal to one means what?
Perfectly
Strongly
correlated.
correlated.
Perfect correlation, 100% correlation. So
Yes.
this is let's take gold for example. So this is today's gold price. Today's gold price. This is yesterday's gold price. This is day before yesterday's gold price. 3 days before, 40 days before. Okay. So I have taken 40 days of gold price data and then I have plotted this one. So this is equal to 1 because today's price is 100% correlated with today's price. That's why you see 100% here. Is it clear why there is a 1 correlation here? Today's price is 100% correlated with today's price. Today's price has this much amount of correlation with yesterday's price. Today's price has minus 0.25 correlation with day before yesterday's price. Is that okay? Is it okay?
Yes.
Okay.
Yes.
So now let us say uh, 10 days. Okay. This particular 10-day before gold price, if it is coming outside this blue region, what does it tell you?
It means you cannot predict that day's or today's price is not correlated with that. Or you can say there's a negative correlation because it's going down.
Okay. The sign
Could
is
be
fine. This
outlier
is
also.
negative. This is positive. But the
Okay.
interpretation here is this blue is the the blue is the significance region. If you see a point lying outside this blue region, it means that that particular value has a correlation with today's price. So if you see a point lying outside the blue region, It means that particular point or that particular day has a correlation with today's gold price. In this data set, we don't have any such correlation. Whereas, let's say you have the 40th day price coming outside the blue region, it means 40 days before what gold price was, it has a correlation on today's gold price, right? That is one of the assumptions of linear regression, where the previous values do not have any impact on your predictions, right? The target variable, the values of the target variable do not influence the predictions of your current predictions of the target variable. Your previous
But
values do
when
not
you're
push or
but
pull
when
the
you're
target variable.
explaining autocorrelation, like if it
Hmm.
is a perfect plus, that means it's a perfect positive correlation. If it's
Yes,
negative, then that means it's perfectly negative. But when it is going outside the particular region, what you have stated,
hmm.
that means there could be a possibility uh, like it is an outlier also as a data point
No,
as
no,
we are
no.
comparing a
This
particular
is a
thing.
statistical function called autocorrelation function, which only tells you what are the lag variables. There is a function called lag variables. You are checking, is there any lag variable that is significant or not? And in this data set, we don't have any points that is significant. That is coming out of the blue region. When you have that,
So only
then
the points which are coming out of the blue region are significant.
yes.
Okay, noted.
So these are the assumptions of linear regression. So you check for first, you check for linearity. You check for, I mean, you can put a scatter plot and you can check for correlation between x1 versus y, x2 versus y, x3 versus y, x4 versus y. You can check whether they are linearly related or not. Is there a linear relationship between your independent variables and your target variable? That is one check. Second check is independence. What is independence? The one that we saw now, right? The one that we saw now. Your previous value, do they have any effect on the current value of the target variable? Okay, if you look at this graph clearly, we are plotting the residuals and we are plotting 40-day lag. You can have 50-day lags, 60-day lags, and so on. Okay, so we have exceeded. Let's keep 30, right? And we have set the significance level as 0.05.
Just one
Okay.
question here, just
Hmm.
like since you have made the base as, +1 and the day
Hmm.
0, say, for example.
Hmm.
So day 1, it is, I could see close to 0.1 or something like that.
Hmm.
So how do this, mathematically, how do you, arrive at this 0.1 compared to 1? So this say today is a gold value is a 70,000.
Hmm.
So that is a 1. And
Hmm.
tomorrow it is a 60,000. So how do you mathematically relate this correlation?
Yeah. How do you mathematically relate this correlation?
Yes.
That's what. We have certain statistical packages that are inbuilt within this function,
Okay.
SMT. So if I have to teach you those functions, it's going to take a lot of time. So since this is a business analytics course, we don't want to get into the statistical part of that. So what
Okay.
we are going to test you, or what we want you to understand, is not how the statistical package is working. We
Okay.
want you to focus more on the interpretation and insights.
Understood. So that
Yes,
means it's basically another statistical package, or
yes,
say another statistical modality of
yeah,
arriving at this figure. So so that basically rates one at say base figure at 1, and then gradually you compare to that. It is like like price index number. You have got a base here. Like compared to base here, what is your price? It is going up or going down, something like that.
yes,
So base, if you consumer price index, what happens basically they correlate to a basically a base number. Is something like that. So you have a
yes,
base, and subsequently compared to the base, what how you change like that. So it is something
yep.
related to that. So
So
that's
assumptions
only
of,
inbuilt in the package.
yep, assumptions of linear regression. So we saw linearity. You could simply plot a correlation plot and check for linearity between your features and target variable. Independence we just saw with an ACF plot, right? And uh, you can also check with this Durbin-Watson statistic. That's another statistical test for checking independence. Second thing is normality. We saw two things. One is a disk plot, right? And then we also discussed about goodness of fit. What about errors? We looked for homoscedasticity. We checked for homoscedasticity and right errors. Do they have any particular pattern, right? So you can remember this particular acronym called line: linearity, independence, normality, errors, right? Errors. Second thing is, and then finally you can also remember multicollinearity. Don't forget this. All right. Okay, I see some people raising hands. Let me take those questions now. Okay. Anybody raised hand? Anybody has any question? Where does it auto correlate? Okay, Bhavna, please go ahead.
So can you explain, sir, Durbin-Watson, how to find the independence from that?
Okay. So it comes as an inbuilt package in. Okay. As a business analyst, let's not focus more on what Durbin statistic test does, but let's uh, try to understand from this particular value what is happening. So Durbin-Watson statistic, it ranges from 0 to 4. If you have 2, it means there is no independence.
If beyond that, it is independent.
Okay. Okay. It talks about autocorrelation, right? Let's say you have a target variable, right? You have a target variable y. Let's have x-axis as uh, 1, 1, 24, 2, 1, 24, 3, 1, 24, and so on. Right? You have data collected over time. This is your x-axis. This is basically time, right? And you have price y as some price. Let's say gram per gram of gold, right? 7,200, 7,400, 8,100, and so on, right? And you are somewhere here, right? You are somewhere in November. You are checking whether yesterday's value has an effect on today's value, right? And for this, you can use Durbin-Watson statistic. When you have Durbin-Watson statistic equal to 2, what does it mean? What does it mean?
No autocorrelation
No
detected.
autocorrelation. When it is equal to 0, positive autocorrelation. When it is equal to 4, negative autocorrelation. Okay, that's all. Okay, these are actually not part of your syllabus. These are some extra things that are good to know. So therefore, getting into the statistical analysis is going to only confuse a lot more people. So it's a good thing to know. And I want to cover another interesting package for you, which will be very useful in your presentations. Can I do that now? We still have some time. I may
And
take.
one thing, sir, I want to ask, sir, you explain X1 is not correlated with X3.
Sorry, can you repeat?
X1 explanatory variable is not correlated with X3.
X1 explanatory variable is not correlated with X3. Is that your question?
Yes, yes, sir.
So you can simply look for correlation between X1 and X3. If they are high, then you can say that they are correlated, and you also have this variation inflation factor. Okay? X1, X2, X3, X4. There is definitely multicollinearity in this data because you have one X1 having more than 10.
Yes.
So therefore, there is definitely multicollinearity. So you cannot simply remove X1. That is what I'm saying. Just because X1 has multicollinearity of 17.54, don't simply remove X1. So you need to check with the business to understand, is X1 an important variable or not? Instead of X1, can you remove some other variable that is highly correlated with X1 so that you don't get into the problem of multicollinearity? So this kind of conversations you need to have with the business stakeholders so that you don't miss out on important information.
Okay.
Okay. Without wasting time, let us try another interesting package called Gradio. Okay. So the coding is far beyond the scope of this subject. This is a good thing to know. Let's understand this and then talk about the coding part. Don't worry about the coding part at all. So I'm loading this data set called Iris. Have you heard of this data set Iris?
Yes, sir.
Okay, some of you would have heard Iris, some of you may not have heard Iris. Let me explain what it is. Okay. Um, okay. So Iris data set is basically a classification problem. You are given certain dimensions of flowers, and with that dimension, you need to classify whether it is a setosa or versicolor or virginica. And if you look closely, they all look similar. It's very difficult to distinguish between setosa, versicolor, and virginica. Do you agree with that? They all look similar. Maybe the colors are different, but
Regarding the size of petals.
Yeah. So you have 4 dimensions or 4 features or 4 independent variables called petals. So these ones are called petals. These ones are called sepals, right? You have 4 things with you called. Let me run this and show you what it is. Iris, one is feature names. Right? Okay. So these are your features. What is a 0? 0 is nothing but sepal length. 1 is nothing but sepal width. This is your petal length and petal width. And with this, what are you going to predict? What are you going to predict? Whether it is setosa or versicolor or virginica. Is that clear? Given these dimensions, you have to predict whether it is setosa, virginica, or versicolor. Is the problem clear? Is the problem statement clear?
Yes.
Any doubts on the problem statement? We can redo it. I can explain that once again. Okay. Okay. What problem is this? Under the umbrella of supervised learning, this comes under which category?
Multi-class
Station.
classification.
Multi-class.
Multi-class classification. What is multi-class classification?
We have more than binary is 2 classes. We have more than 2 classes.
Okay. So when you have 2 classes 0, 1, it is called binary classification. So now you have 3 classes. It comes under the umbrella of multi-class classification. So when you have multi-class, what kind of algorithms can you use? Can you use logistic regression?
So we need to put the proper parameter, which is multi-class equals multinomial using sklearn.
Okay. Can logistic regression do that?
So so we have to put the multi-class equals multinomial. There is a parameter.
Okay, I get it. So generally, what is the activation function that we use for logistic regression?
Sigmoid.
Sigmoid. Can sigmoid do that?
No, sir.
Okay. Sigmoid can only predict 0 or 1. So therefore, you need more sophisticated activation functions like softmax. So these are certain activation functions that you will come across in due course of time. Don't worry about it now. Right now, you understand that logistic regression is using an activation function called sigmoid, and it can only predict 0 or 1. Is that clear?
Yes.
Logistic regression with the sigmoid activation function can predict only 0 or 1, and it cannot predict 3 classes. That's the takeaway. Okay. With that, I'm going back. Okay. So therefore, what I'm doing here is, since you are not introduced to multi-class classification, I am not going to treat this as a classification problem. I'm going to treat it as a regression problem. What will happen if I treat it as a regression problem? What will my predictions be?
They'll be real values.
They will be decimal values or floating values. So my y pred for this value could be something like 0.123. Here it could be 0.281 and so on, right? I'm going to get my output in the form of a floating point value. Is that clear?
Yes.
Okay, you have your X as you have 150 rows. This is X1, X2, X3, X4, sepal length, sepal width, petal length, petal width. And this is your target variable. And we are going to treat this as a regression problem and then do the train test split. Is this okay? Have you heard of this term called pickle? What is pickle? What does this
To
do?
save files.
Okay, what files?
Model files.
Model files. Very well said. Okay. So what I'm doing is I'm building a model called linear regression, right? And I'm storing it in lin_rrhd. And then I'm fitting this regression model to my train data. Are these two lines clear? Are these two lines clear?
Yes, sir.
Yes,
Okay.
sir.
Then this again, this pickle file is out of syllabus, right? It is out of the scope, but it is good to know. So therefore, if you don't understand, don't worry. What I'm doing is I'm going to save this regression model in this pickle file. So if you go to my data, previously we had, right? This is a data that has been imported from sklearn.datasets, right? After this particular line of code, my regression model is stored as a pickle file here, right? You can download and keep this file. And if you open it, you won't be able to understand anything. Pickle file is not readable. You won't be able to open and see what is inside. It is a model. Whatever model you are building, you are saving it as a pickle file. Why? That we'll see now. Right now, forget the pickle file. And you are making predictions on your X test. Is this okay? Is this okay? Simple prediction on your X test. So far with me?
Yes, sir.
Okay. So, I mean, this is just a demo class. This is not a part of your BA course. This is a good thing to know. Don't panic if you don't understand what is a pickle file, what is Gradio, and so on. It is just a demo. Okay. You can definitely understand what is this. Just ask ChatGPT what it is. It is going to give you everything. So now what I'm going to do, I'm installing an app called Gradio, right? I am importing my pickle. So this model, which has been stored here, I'm going to open it now, right? I'm going to open it now and let's see what it does, what this one function is going to do. Okay. What does this tell you? I'm going to increase my sepal length, reduce my sepal width, increase my petal length, submit. What is happening? What is happening?
Predicting the
So it's
class.
predicting.
Predicting the class. Okay, so I'm going to click on this particular URL and then I'll come to that function part. So generally, when somebody gives you a regression problem or classification problem, what do? How do you give them the output?
Confusion.
In the form of a Excel sheet where you give your predictions to them, right?
Yes, sir.
But this is a better way to present your model to your stakeholders, right? Instead of just giving them an Excel file with all your predictions, try to build this kind of an app and give them. It's going to impress them a lot. Save their time. They don't have to check what is what, how to predict, and so on. They will simply play with the parameters and get into predictions. Right? Is this useful? Will this be useful for your presentations in the future?
Yes.
Yes, sir.
Yes, sir.
Okay. So now let us go into the coding part. So don't worry if you don't understand this code. It's totally fine. It's just an extra thing. I'm simply writing a simple function called predict. What are my parameters? Sepal length, sepal
The
width,
four
petal length, and
features.
petal width. Okay. And there are 4 inputs to my model: sepal length, sepal width, petal length, and petal width. Right? And what is this? What is this lin_rrhd? And
Linear regression.
Our model.
how do I fetch it? How do I fetch it? From the pickle file. It has been stored in the pickle file. I'm just getting back this from my pickle file, and I'm predicting on my input data, right? And here I'm rounding off. When I get value close to 0, call it as setosa. When I'm getting values close to 1, call it as versicolor. And then greater than 2, call it as virginica. This is how I'm telling my app. And here I have 4 parameters: sepal length, sepal width, petal length, petal width. I'm going to get input from the user. I say the minimum value for this is 4, maximum value for this is 8. And if you go to the app, right, this is 4 and maximum value is 8. Okay. And similarly, the default value is 5 here, 3, 3.51 here. I'm also giving a label here. And my output is going to be in a text box, right? And once I run this function, I will have a dedicated URL that is going to be live for 72 hours. Okay. And again, be very careful. Just because you know Gradio, don't simply go and host it in a public forum, because certain companies have restrictions. You cannot play with your company data in a public forum. So be very careful, but you can locally deploy it within your system. So be mindful of all these things and then try to use it in your workspace. You can use this for anything. Gradio is an app that has been purchased by Hugging Face. How many of you know Hugging Face? Okay, you will know all those things in the coming days when you take courses like LLMs, GenAI, small language models, and so on. So it's a very, very powerful app to show all your results in an interactive way, right? I think I've exceeded some time today, but let me stop sharing. And
In
now
which cloud the data or the model will be loaded with the gradient, sir?
they have their own server. You can
In
use.
the
I
Gradio
mean,
you will use, sir?
yes, Gradio have their own server, and it would be live for 72 hours, and your model also has to keep running. And if you stop it, this will go up. So this is very useful for showing your results in an interactive way. And tomorrow, this is useful whenever you go for interviews. Tomorrow, when you go for an interview, it's very okay. Let me also stop sharing because we've exceeded the time. I'll stop the live stream, and then we will have a little more discussion. And officially, the live class is over. People who want to drop off can drop off. People who have questions can stay back and get your questions clarified.